You posting it on Discord. Okay, so you put something. This is not the right one. Who put this? No, I'm talking about this one. Is it because we are not in selection mode? Not in selection mode? Someone posted it here without. Okay, we start in 10 minutes, okay?
They can even create clips. I mean, anyone can create a clip.
Amazing. We will start. We will start in 10 minutes. Yeah, like 5-10 minutes we'll start.
First screen को चलेगा ना? Next करेगा?
Who? Please come.
Hi everyone, thanks a lot for joining us. We'll be starting in like next 5 to 10 minutes. Okay, hi everyone. Thank you for joining us. For those of you who are joining us physically here and the ones that are joining us virtually, thanks and welcome to APRA's meetup on motion estimation strategies on Nvidia Jetson. Um, I'm your host for the day. My name is Shriyuta Srivastav, and I'm a software engineer at APRA Labs. So, uh, so uh, before we start, I'd like to give you a brief introduction on APRA Labs. For that, I'd like to call Mridul here. Mridul, please.
Hi, I'm Radul. I've been working here since 2019. So, if I have to describe Apra Labs, I would say it's a non-VC funded, profitable company that specializes in anything related to computer vision, image processing, or streaming. And we have been working in several domains. We have worked in healthcare, in surveillance, and authentication. So if I define the visual range of the kind of problems we solve here, it ranges from few hundred micrometers to few hundred square feet. So it's a range of problems that we solve here. And apart from just using classical image processing methods, we also employ a lot of AI and ML. We have developed a lot of models, novel models on our own. We have also focused a lot on uh, getting the best performance out of the existing models if we end up using them. And actually, our previous meetup was sort of about that. We talked about byte track. It's a object tracking model, and we optimize it using NVIDIA TensorRT. And in the last 2 years, we have found ourselves developing a specialization in edge computing using mostly NVIDIA devices. Again, Jetson or Jetson Odin, it's a host of devices, but not just NVIDIA Jetson. We have also experience in other boards like Google provides Coral. uh, and what we have found is that we have sort of reached a specialization part where we found ourselves reusing a lot of code and solving similar problems again and again. And we found that there was no easy way, easy existing way, easy customizable way to reuse our own code or use all these libraries that we are frequently using. So we started developing our own framework, which is called Epra Pipes, and we'll show you a demo based on that today. And so it's a framework. It can be used for image processing, video processing, even audio. You can do text if you want to, because it's pretty flexible. It integrates most of the libraries that we frequently use, or most of the libraries typically anyone will use in image processing mainly. And so today's meetup, it is about motion estimation, and the code is written in our framework. The preference will show you. It is kind of, we chose it because it is a sort of follow up of the previous meetup, which was about object tracking using bytrack and Nvidia TensorRT optimization. However, if you have not joined the previous one, it is not going to affect it. It will be completely compensated. I hope you have a nice day.
Thank you, Mridul, for that. Right now, we'll be moving forward with an ice-breaking session for those of you who are here physically. For that, you will just have to come over here, introduce yourselves in like 2 sentences, and pick up a chit that we have right over here and answer whatever question comes for you. So, anyone of you can start?
Yeah, the question is, how do you recognize when you're stressed? My nickname.
Okay. Can you just give a short introduction?
I'm Anand Nehru. I'm a data scientist at Reliance. I work for the computer vision team. We mostly use object learning. We use all the computer vision environments to build for IPL. Next year you'll see IPL computer vision covered. And we are also working on visual search, making visual search better using a bunch of
Thank you.
If you could safely eat any inedible object, what would be ragi? Ragi dosa or something.
But that's already edible.
Edible or not? I don't know what is that.
Like some people have this craving of eating rubber.
No, I don't have such things. Maybe I can chew some gums, but
Okay, like a small introduction.
yeah. Myself, Saravanan. I used vision systems at my earlier career when I was doing industrial solutions. Mostly industrial vision solutions I provided. Mostly solutions from Japan or US. Right now I'm into renewable energy industry. I'm a controls engineer. And we are looking for a solution because in the wind industry, the quality will never get, the quality inspection will never get over a factory. It goes to site also. So nowadays, in our industry, people are looking for the vision-based solutions where you can monitor the quality of your product at site. So that is where several people are developing such solutions now. So I'm curious to know about you guys. So that's the reason.
Okay, thank
Thank
you.
you. Thank you.
Yeah, the question is like, what age phase do you wish you could be permanently? So whatever I'm living, I want to be in that same phase only. So basically, I'm Yashraj. I work as a full stack developer here. I work in embedded applications, like where we develop healthcare systems. And all. Yeah. Apart from that, I like work on video streaming engine also. That's what I do.
Um,
So the question I've got is tell us about the place you belong to without specifying the name. So I come from a very remote place, not very famous, but I can tell that it is uh, a center for tobacco in Karnataka. It's like, yeah. So my place is the king for producing tobaccos in South India, the whole of South India. It is mainly exported for bidis. So it's called Nippon actually. It's not very so famous. So my name is Mohammad Zaki. I am working since past 1.5 years at Apple. I am I am working on the framework that Mrudul just told. It is mainly on video and image processing. So I work on that.
Yeah. Myself, Nitin. I'm an Android developer at Apple Labs. I'm working since 3 years. So basically, I work on Android applications and some Spring Boot applications. So, question for me is: if you had to delete all but 3 apps from your smartphone, which one would you keep? So one football app where I get all the updates. One like where I can see all the videos like Hotstar or something streaming. And the third one can be something like social media,
Which one specifically?
specifically threads, which is
Hello everybody, my name is Siddharth. I think the question. So, what's your favorite vacation spot and why? Near Bangalore. I've been to a lot of spots. Uh, I think it's Yarkut. I like Yarkut. Which is in, so, I've been to Yarkut 2 3 times, and it's very nice there. It's the drive there on the roads is very good. I am currently I'm working with Apple Lab since 4.5 years, and I am currently as a full stack developer plus an architect. So we build microservices applications, scalable microservices applications, and now I'm venturing into Apache Spark and ETL.
Hello everyone, my name is Vishwanath. I'm working as an intern since 4 months in Apple Labs. Question is, if you could eliminate one food so no one could eat it ever again, what would you what will you destroy? Bindi.
Hello, my name is Vishal. I'm working in Apple Labs since 1 year as a software engineer. So I mainly work on mobile application and Spring Boot applications. So my question is, which movie made you laugh hard? I think therapy.
So I guess we can proceed further with our session. Um, yeah. Okay. So I guess we can move forward with our session, and Yashraj will be coming over from here to present.
Thanks, Shweta. Okay.
Like this is your host Yashraj. I'm going to point out some interesting things about this motion estimation strategies, which we have done on Nvidia Jetson. This is powered by Abra pipes. So before going into the slides, let's first look into the agenda. On I don't know like how many of you have attended our last meetup, but we'll quickly go through the object tracking regulatory strategies, whatever we have used. Followed up by motion estimation, what basically motion estimation is. Then we will go to the motion vectors. Don't get overwhelmed. We'll just in the coming slides we'll go into the what all concepts are there. Then we'll go to one of the basic compression technique, which is S264 encoding, and then we'll show you a demo just to get the concepts more clearer. Then we'll show you our framework which we have used to create this pipeline. This is MRS. This is our in-house framework which we have developed over 15 years of in-house framework. Then it's followed by quiz and Q&A session. So let's get into the slides. Okay, so so in our last meetup, we discussed about Wi-Fi. So the audience who has not attended the last session, I'll just go through it brief. Wi-Fi is a object tracking model, which is basically a machine learning model which is used for object tracking. However, it's important to go through a case where like motion is not frequent. Consider a scenario. So suppose to consider a time like it can be a night time where motion is like very infrequent. That time, if you run a machine learning model, so it will be a wastage of power because as we all know that running any machine learning model requires a lot of computational overhead. So it would be good if you have a rough estimation of motion so that we can avoid inference on those frames where motion is not there. This can help reducing the cost of running the system because it will be basically a layer over it. So if it will pass, like if we're just able to get through that, like we have motion or not, so that we can easily go to the next step, which will be the inference part. And if motion is not at all there, then there is no point of inferring that frames. So through that, like we can make it more optimal. We'll show like how we calculate this motion vectors and all, and how we'll estimate the motions in the upcoming slides. ByteTrack can go as fast as 200 FPS on Nvidia Jetson, which we have tested. We have done a benchmark on it. Okay, so what is motion estimation? Let's first look into this video. If you'll see this video, you'll find these red arrows. Don't know what this is. So what does this arrow signifies? This arrow signifies how much the object is moving and in which direction is moving. So as you all know, like vector is nothing but it's basically a quantity through which we can identify the direction as well as the magnitude. So it contains both direction and magnitude. So this vector also shows like in which direction the objects are moving in, like what's the magnitude of it. So if you look into these objects, you will find that arrows, the magnitude of that arrow bigger, and it will gradually decrease when it will move apart. So this is because like it's easily able if you are easily able to get the motion here in comparison to the objects which are far away. So what is motion estimation? Motion estimation is an algorithm aims to quantify the motion sequence of frames. Such information has wide-reaching implication in compression algorithm that are temporal in nature. Here, temporal signifies time. More specifically, in video processing world, the term motion estimation refers to the calculation of motion vectors. How we calculate motion vectors? That's basically defined by motion estimation. Motion vectors describe the transformation from one frame to another. So if you look, object in first frame is here, and like maybe in the second frame it will move apart. So how much transformation is there? That is basically defined by motion vectors. Now let's look into motion vector. Motion vector is calculated by finding a correspondence between rectangle at time t and rectangle at time t minus 1, where t is the frame index. I will not go into the in detail of it, but I'll show you a glimpse of it, like how actually motion vectors are calculated. So what we do, basically we divide our image into macro blocks. Typically it's 16 by 16 block. It can be anything, it's configurable, but generally we prefer 16 by 16. Then what we do is like we take one of the macro block and we move over the 16 by 16 blocks and we see where the deformation is less. So that is our best fit. So wherever the deformation is less, that signifies that object has moved in that particular direction. So suppose my hand is here, in next frame my hand is here. So if you look into the deformation, this particular block will have the least deformation in comparison to the other blocks. So that's how we see how motion vector is calculated. The motion vector informs the delta change across the frames, like how as the frame change. This transformation can be encoded using less bytes per pixel as compared to the actual original data. Hence, we can achieve temporal compression because we are able to reduce the size of the data what we are storing. This is the idea behind video encoding standards like S264. This motion vector and motion extension are basically used while doing that S264 compression. Okay. Now let's move toward S264 encoding. S264 encoding is most renowned compression technique. But before going into encoding, let's take an example where you want to record a 20 minutes video and you are getting a frame with a source of 640 resolution, which is running at 20 FPS. So if you just store a single frame, it will be around 640. The size of that particular data will be 640 into 480 into 3 for a single frame. And if it's running at 20 FPS, then in a single second, you have to store 640 into 480 into 3 to 20. So if you want to store 20 minutes of data, it will be roughly around 2 GB. And suppose if you want to make it 1 hour, then it will go high. So for storing this 20 minutes of data, if you are consuming this much of space, then it's not good. We need to make it efficient because it can't be available in other drives. Like if you can't have a SSD and you can record a 2 hour or 4 hour video. So we need to make this encoding work. So what does this encode? We'll look into this S264 encoding. S264 is a motion compression standard. This algorithm performs both spatial compression followed by a temporal compression. Spatial refers to space and temporal refers to time. Okay. So now let's look into the spatial compression. Let's look into this image, these 4 frames. First of all, this is the original frame what we had. We have extracted the luminance part. Luminance is basically the black and white component of it, and followed by the blue prominence and red prominence. The blue component of the image and the red prominence of the part of the image. So if you see, like you will be able to easily get most of the things from this luminance in comparison to this blue prominence and red prominence. So the idea behind is that our eye is more receptive towards luminance in comparison of prominence. So that's why you are able to get most of the things in that luminance. So the idea behind spatial compression is because this data is useful, but you are not able to make most of it. So even if you downsample it a little bit, then also it's fine. So what we do in spatial compression, we go through 2 layers of, not basically 2, we go through a series of algorithms where first we convert the image into pi CBSAR. Pi CBSAR is nothing but taking a luminance part of, and then taking blue luminance and then taking the red one. That we do in order to separate the luminance from the other part. The spatial compression can be achieved by chroma subsampling because even if you just downsample this data, the video quality will not affect much. So we can easily do the downsampling. So that's how we can, in terms of space, we can reduce some. In terms of space, we can just optimize it, but that will be not much. So we'll go through one more interesting thing, which is the tabular compression, how tabular compression works. Before looking into this tabular compression, look into these 4 frames. You will find that most of the things are static. The only thing which is moving or which is changing is this flow of water. And I don't know whether you are able to see this person or not, but the position of this person is also changing. But apart from that, the cliffs and all is remaining static. So if you look into the idea behind it, what we're doing is like we are storing one keyframe, and then we're just storing the difference of this frame and this. So if you look in this frame, only this water flow is changing, and the position of this person is changing. So we are storing only this data. So we are storing a data where actual motion is there. We're not storing the other hidden part. So also, if you look into this room, in this room, the only thing which is changing is like all of us. But if you look into this wall, all of them are static. So there is no point of having this like in every frame. So in one frame, we can store all the data, and in the upcoming frames, we can store the difference of it. So that's the basic idea of temporal compression. So we can achieve greater compression by avoiding the part of the frame where motion is not there. Uh, so as I discussed, like we basically divide our frame into 16 by 16 block. Where we first wrote the first frame, which has lot of data, which can almost contain the same data as the actual frame, but it's intra-frame where spatial compression is done. But apart from that, we store all other bytes, bits. This we store to reconstruct the other frames. Then we store the other frames, which is basically the difference. So in order to generate this frame again, what we do is like we just copy this part of it into the first frame, and we will be easily able to reproduce this second frame. And same, we can just generate third and fourth. So basically, this is difference between first and second frame. This is difference between first and third frame, and this is difference between first and fourth frame. Um, so it imports one static image, iframe. This is full frame containing all the bits it required to construct the frame. The subsequent frames are either P frames, predicted frames, or a P frame. P frame we basically use when we are having that video recorded, and P frames when there is live stream. B frame is more optimal than P frame because we have a two-way communication. So through that we can have a better idea of that. B-frames are frame that will encode a motion vector for each of the macro blocks from the previous frame. So a B-frame has to be constructed by the decoder based on the previous frame. So that basically generally means that through this frame you can easily generate. If you have this and this frame, then you can easily generate the second one. And if you have the first and third frame, then you can easily generate the third frame. So that's the whole idea of having this S264 encode. So through this we are able to make the space lesser, which is more important in today's world because we are using this embedded application and all, where this embedded device doesn't have a lot of space to store. So we have to do this compression. Anyways, we have to do this. So this is the whole idea behind this. Right? Now we'll walk through the demo. Zaki can show me them.
So here we all see uh, the live stream is coming from that IP camera, and it is getting processed through the module called as motion vector extractor. And if you see, the motion vectors are getting overlaid wherever the motion is. if you see wherever the motion is, it gets overlaid and then displayed here. So this pipeline is basically coming from that RTSP cam, IP cam basically. So the demo that we saw just now, this is that. So this is that pipeline. So basically, what we are trying to achieve here is that to get motion vectors from S264 encoded bit stream. So here, if you see the pipeline, we have RTSP cam source. Nothing but RTSP is nothing but real-time streaming protocol, which gives S264 encoded frames. So it is able to stream frames from any IP camera that has S264 chip in it. So which has S264 chip to encode the frames, and then it is connected to motion extractor module. So this motion extractor module, what it does is it extracts motion vectors from X264 frames, and this the motion vectors are then sent to overlay module. So whatever motion vectors that we get, the motion vectors are then overlaid on this on the frame in this module, and then they are finally getting rendered. So that what we saw just now. And to emphasize motion extractor module that we have developed, it can only and both extract motion vectors and decode frames. So it has capability to do one or both at the same time. And overlay module is just a module to overlay this motion vectors on the decoded frames. And one thought process here is that any camera that has H264 codec or hardware accelerated with chip in it, that is inherently capable of doing motion estimation. So coming towards comparison, so this slide sort of explains the comparison between FFmpeg and APRAPeg. So basically, FFmpeg, if you all don't know what FFmpeg is a global standard. These are into image and video processing. So they have a wide range of pipelines. So basically, H264 decoding, I can say that H264 decoding can be divided into mainly two parts. So one is bit stream decoding, and then there is frame reconstruction. So if you follow the FFmpeg's approach for extracting motion vectors, so what they follow is that they get the H264 bit stream, and then they decode the bit stream to get motion vectors. So once we get the motion vectors, they can be applied to reverse the process of whatever H264 encoding has done. And then from that information, we actually reconstruct the whole frame. So whatever the frame that Ashraj showed, the waterfall one. So the difference, whatever is there, is stored in basically in motion vectors form, and the whole frame reconstruction for P frame happens in the second process, which is frame reconstruction. I can say that frame reconstruction is a very compute intense task, and it roughly calculates. It roughly is 60% of total decoding task. So if, for example, if someone only wants to get motion vectors out of H264 encoded bit stream, so there is no sense of having frame reconstruction in that phase, and we can just skip that part and just extract the motion vectors. But this was not possible through FFmpeg. So we came across one approach, and we designed one module which ultimately skips frame reconstruction part, and it only extracts motion vectors from an H264 encoded bit stream, and it saves a lot of CPU capacity and the compute intense task. And yeah, so this was our approach of doing a better solution than what FFmpeg has done. This is a latency performance benchmarking that we have done. So we had a video which was of resolution 1920 cross 1080. It was a 2K resolution video, and we did this benchmarking. If you see, this graph represents motion extraction time versus GOP in the video. So to emphasize on GOP is nothing but a group of frames. So I frame, the independent frames, and the combination of P frames. Whole this bunch of frames is called as GOP.
Is
So
it like batch mode?
sorry.
Is it like batch mode of operation?
No, GOP is basically so as we saw, you have I frames followed by P frames, and then this whole thing repeats, right? So this unit of I frame or the P frames repeats itself. So this group of pictures is just
Yeah. So this we had this video, and this video had around 90 GOP, you can say. We performed an operation, and we came across that for extraction of only motion vectors from that frame, FFmpeg took around 90 to 95 milliseconds to complete one GOP task, and whereas the solution that we have developed, it took only around 45 to 50 milliseconds of the same job to do. So we can say that it is very fast in some manner, and it has some very good latency also. This is the benchmarking we did for CPU usage performance. Uh, this was we tested this same video across different FPS at 30 or 90 and 1 till 180. So we saw that in the FFmpeg's approach, the CPU usage was quite high, and whereas the solution designed by us, the CPU usage was ultimately very low as compared to FFmpeg. So we can also say that our approach is also very CPU friendly. It took very less processes whereas compared to FFmpeg. So the main thing here I would like to say that if someone wants to design the surveillance for a system, and what generally surveillance means, you are getting streams from an IP camera and you are directly storing it on the disk as MP4. So there is no need for there is no place for decoding happening here. You are just getting H264 frames and you are saving on the disk. And if you also want to say that I want to have some setup for surveillance where I get kind of data where I need to know if some motion is happening at that place. For example, warehouse. In warehouse, we generally see no one comes and out usually. So at that time, full decoding is of no use actually. If you want to just extract motion vectors from that stream, we can use our solution, and then it saves a lot of CPU time. Yeah, this is also one performance approach. So as Esra discussed about the ByteTrack TensorRT. So basically with TensorRT optimization on GPU, ML likes algorithm which but ByteTracks can run at an FPS of 200. And for similar resolution, the solution designed by us can run as fast as ByteTrack, but it is purely software based. It has no involvement of GPU in it. So we are not claiming that the motion estimation algorithm that we have developed can replace ByteTrack, but yes, it can be applied as a pre-filter on before sending those frames to ML module. So if there is no motion, we can just save the ML compute task and save the CPU intense task there. So this module that whatever we have developed, it can be a good pre-filter for the ML based solutions where there is no motion. We can skip that. We can skip ML based approach for those things. Yeah. So we have one demo too now.
All of you must be wondering where this demo is running. So it's running on this AGX. Able to see it or not? This is Nvidia's AGX, which we are running this demo. And, and this is doing exactly what that RTSP camera is doing. So if you just move your hands, you'll be able to. No, basically it's detecting the motion. I'll just keep it constant and show you because you see a lot of noise. So if you look into my head, it's basically tracking the motion. And there are a lot of noises on it. Like it's a parameter which we can change. We can make it high, we can make it low based on the usage what we have. But yeah, that's a general idea. It's basically used for detecting motions. And that motions can be used as a first filter for performing any pipeline or any heavyweight machine learning model. So it will be just add a filter over it.
So what you want to emphasize is that we talked about in the previous camera, we talked about camera if it has capacity issues for so no, it's a simple web, right? You can do this with your
So any camera or say any simple webcam that is capable of giving raw frames is also capable of having motion estimation for that camera. So this is a very simple pipeline. If you see, just a webcam is capable of doing such compute intense tasks very easily. Yeah. So we'll discuss about this pipeline we saw just now. Uh, so we have a webcam source which is connected to a S264 encoder. So the S264 encoder is this, which is running on this Jetson EGX, and the same pipeline. After that, we have one overlay module which overlays the motion vectors that we get from S264 encoder, and then it is getting rendered. So the main thing here to emphasize is that apart from H264 encoding, we can also get motion vectors as byproduct of H264 encoding. So, anyways, if we see that in S264 encoding, motion vectors plays a major role. So, the main idea here was that so during that process, why can't we just extract motion vectors out of it and make use of it for surveillance and other things? Yeah. So here we have developed this module for doing both the jobs, S264 encoding and motion vector extractor. Uh, the legacy way of doing this was frame to frame difference, which was getting expensive for CPU related tasks. So this pipeline is meant for some simple webcams, those who cannot afford such big IP cameras and the costly cameras. Even with some simple webcams or any other cameras, it is capable of doing motion estimation. So now about Opera Pipes.
Yeah. So APRAPEP is a pipeline framework for developing video and image and audio processing applications. So whatever pipeline you have seen, like through this session, all of them has been created using APRAPEPs. APRAPEPs is our in-house framework, which allow us to easily create this pipeline. It's easy to use, and the best part of it is like it has been created by our founder and other team members who have been working on that for last 15 years. So the other interesting part of this is like everything is highly customizable. You can customize, like as I said, like that noise thing is a property. You can easily change. It's a property just like that. Like you can have lots of customization as per your requirement. The other good thing is that it runs on like lot of platforms, like almost every platform. Like Windows, it can run on Windows or Linux or any of these embedded devices. Currently, we are running this demo on this Jetson AGX, which is an embedded board. It supports multiple framework like OpenCV and PPI, and it's like easy to make. It, it makes it easy to use complex library. Like suppose if you want to use OpenCV, then it's easily available to integrate that module into your Aprapa's module, and then you can run through it. Also, like you can use NPPA libraries and all. So this is our Aprapa's in-house framework. So basically, it has three layers of um, blocks. Where first one is the source. Source is nothing but where you get the frames. It can be a camera source, or it can be from a file, or it can be from MP4 video. From wherever the frames will be generated. Then on those frames, you will do a lot of transformation. You can do resize, you can do rescale, or suppose in our case we are doing that motion extraction. All those are part of transform. There can be a multiple transform, there can be multiple source, and there can be multiple sync also. In our case, in sync, we are using this EGL render to render those frames. So as I said, like you can have multiple sync. One sync can go to that renderer, other sync can go to a writer, which will write that MP4 file. Other can go to a file writer, we can just write some of the frames. So this is basically about Aprabytes. If you want to go to it, it's an open source framework. You can try a lot of things. This one is a GitHub repo. You can see lot of modules are there inside this particular repo. And also we are building this on Windows, Ubuntu, ARM is nothing but this Jetson devices. Uh, WSL, even you can just download a Docker image and run this whole demo and all. So yeah, you can go through it. It's a open source repo. You can explore it. Even you want to make some contribution, you can do it. You can just raise a PR, you can do, or if you directly want to use it, you can use. And there is a good documentation on it also. You can follow it to build Zappa apps. Okay, uh, enough of discussion. I think. Jackie, you want to show about this?
Yeah. So the demo one that we saw, that the feed that was coming from the IP camp. So that whole pipeline that we saw is just this 4 to 5 lines of code. So it is very easy to use, highly customizable. So just to explore.
Can you meet the slide?
No,
I mean, copy it's an image.
it's an image. It's an image actually. Now is it visible?
Still not visible?
No.
Okay.
Source code.
Yeah.
So copy and paste that is there. Yes. Yeah, this one. You have from his head. In our
Yeah.
yeah, now you can zoom out. Sure. Zoom. Zoom the button. You could have taken
This works. This is visible, right? Yeah. So the pipeline that we saw for demo one. So just to explore, this is a simple pipeline. First, we have this RTSP client source module. So RTSP client source module is nothing but it is able to stream any frames from any of the IP cameras. You just provide the URL for that camera, and we can fetch the frames, history 4 frames from that camera. So the next module that we have is motion extractor module. So this module basically does the extraction of motion vector from this from the frames that we get from RTSP camera, and then we have overlay module, which basically overlays the motion vectors on the frame, and then the module is again going to EGL renderer. So EGL renderer is nothing but a module to render the frames on screen. And you might be wondering how these modules are connected. So we using this set next method that we have, we just do set next from the previous module to the next module, and it connects the pipeline. So in this case, RTSP cam is connected to motion extractor using set next, and then motion extractor is again connected to overlay using set next, and then overlay to sync. Sync is nothing but this EGL renderer. So this is we can say that this pipeline is very easy to use and very easy to modify also, and it is highly customizable. Here, instead of if someone wants to extract motion vectors from MP4 video, we can just change the source from RTSP client source to the MP4 reader. He will be able to do the same job from a recorded video and do the playback using motion vector extractor. Yeah, and this sync can also be modified if someone wants to save these frames on disk instead of using EGL renderer. He can use our own module MP4 writer, which writes these frames in the form of a video on the disk. Yeah, so anything highly this pipeline is highly customizable. User can use according to his use case. Is this visible? No? No. So this is the pipeline that we saw for the demo 2 using webcam source. So here the first module that we have is NP-V4L2 camera source. So this module is designed to fetch cameras from any of the webcam that we have for our computer. So this module extracts the raw frames from the camera and then it sends to S264 encoder module. So this is the same approach. You send this, you do the settings. So this NVV4 module goes to S264 encoder. So this S264 encoder module does S264 encoding on these raw frames, and it has this props called the enable motion vectors. So if someone wants to only uh, encode the bit stream and not extract motion vectors, so that is customizable. And if he wants to extract both the motion vectors and do S264 encoding, then you can just change this prop and he will be able to get both the S264 frames and the motion vectors. Yeah, so then the frames that we get from S264 encoder goes to overlay module, where basically we the frames that we get from camera, we overlay the motion vectors on them, and then we send this frames from overlay module to EGL render, and then we render on screen. Same pipeline, there's just that the source has changed from RTSP cam. Instead of using RTSP cam, now we are using NVV4 into camera source, which is nothing but to extract the frames from uh, any webcam. Yeah, so the main point to highlight here is that this whole pipeline is easy to use and customizable.
Yeah, as Sarkis has shown, like there are lot of customization that you can do. Suppose if you look into this camera source, currently it's set the resolution as 1280 720. If your camera supports 640 480, you can specify that. This is the color transformation that you are doing to just pass through the next module, which is that overlay module. So basically, you can convert our frame from one form to other, one image type to another. Currently, we are converting it from YUYV to YUV420, or converting it from YUYV to BGRA. Based on the requirement, you can change. And same to the render, like how you want to render. If you want to render in a small frame or you want to render in a big window, all those things are customizable. And if you're just looking to this code, it's like hardly 10 or 15 lines of code, and you are able to estimate the motion. So what is like it's good having those two. Now, if we're done, we can move to the quiz round. So these are the basic simple quiz. You can answer it. How do we propose using the motion estimation based on motion vector? Using independently, using as a first filter layer before using ML models for motion detection in surveillance, or all of them. Sorry. Yeah, and yeah, all of them was correct answer because we can do all of the things, right? We can add as a first filter, even we can detect the motion in surveillance. So absolutely all. Why does chroma subsampling work? Because first option is UI line is more sensitive to black and white information than color. The image size is smaller than in YCBCR format. Blue prominence is least receptive for human eye. On all of them. Yeah, correct. S264 encoding involves performing spatial compression, temporal compression, motion compensation, or all of them. Yeah, correct. What can Abra Vibes do? Decoding S264 videos and rendering, record MP4 videos from camera or files, using CUDA libraries for utilizing hardware acceleration by GPU, create overlays on existing videos, or all of them.
We have a couple.
The next one is interesting. This one is little hard. You can just think over it. Which scenario is the best use case for using S264 compression? Medical applications, industrial quality control, OTT video streaming, or all of the above? Think on it before answering because it's little tricky. Huh?
Medical
OTT videos.
The best use case.
Yeah, OTT video streaming. Because why we don't prefer S264 compression in medical application? Because while doing the surgery, right, the movement will be allowed. So that time, if you just take the difference, then it's hard to regenerate the next frame. So that's why we usually don't prefer S264 compression when doing medical surgery. So the answer is OTT video streaming. If anyone has any questions, they can ask.
We interested on the industrial quality. So can't we use
We can't use compression because no one prefers compression while doing industrial quality. So you want as the frame as it is.
And whenever you do compression and you want to decode it to the original, it is possible that that process itself will produce the artifacts, which you may detect as quality issue. So nobody wants compression.
So the first phase of S264 encoding is a logic compression, right?
Yeah.
The special compression, instead of it talking, we remove the colors, which are less sensitive to our eyes.
Okay, that's it then. Anyone has any questions?
Any questions, please?
There's occlusion problem with that, right?
Yeah.
Any approaches to solve it?
Occlusion can be solved. It's because we are not solving motion tracking. We are saying that we are adding a filter before doing motion tracking. Through which we can optimize the CPU performance and the overall we can reduce the performance overhead. So that's what we are doing. We are not saying that we do occlusion.
Can you repeat the questions for online?
Okay.
Just give them a chance.
So
So just read it up now.
okay, how do we propose using the motion estimation based on motion vectors? A, using independently. B, using as a first filter layer before using ML models. C is like for motion detection in surveillance. And D is all of the above. Second question is, why does chroma subsampling work? Human eye is more sensitive to black and white information than color. The image size is smaller in YCBCR format. Blue chromance is least receptive for human eye. Or D, all of the above. Third question is like S264 encoding involves performing first spatial compression, B, temporal compression, C, motion compensation, and D, all of the above.
Not these questions. Okay. It's fine. Okay.
Right.
You can have the.
This was
This question, no, you have to. You need to start answering now. What is the question?
okay.
Oh, the occlusion question, I guess.
Yeah.
Okay. So the question is related to occlusion. So basically, using this motion estimation, we are not saying that we are going to replace motion tracking. We are saying that it's a layer before this motion tracking. We'll do this motion estimation, and if you see if actually there is some motion, then only we'll do the tracking part. Otherwise, we will not use our hardware for making no use of it. So we'll only do the tracking when there is an actually in motion. And yeah, that's the question there.
Yeah.
Anything there? Anyone any questions? Okay, so I think we are done.
Do the slides. Huh? Next video.
Yeah. So thanks for coming. Thanks for spending our time here.
Wow.
And these QR code, by the way, they are generated using similar filters.
So please share your feedback. You just scan this QR and give your feedbacks.
Are those buildings?
Yeah.
Buildings?
Yeah.
So hospital in Bangalore.
So thank you all for joining us here. You can, as Yashra just mentioned, you can scan the QR code for your feedbacks. And if you want to get more, material related to this meetup and get updates on our upcoming meetups, you can just register yourself. We'll use your details to send out mails and invites to you. So thanks for joining. We can have a break now. We have some snacks arranged for you. Please help yourselves.
Switch on the lights.
So our next meetup will be 8/23. You guys can join up. We'll be sending you invites. You can just register using this QR code or the one kept on the table there.
Eight.
Eight August.
No, it's on 5th August. On 5th August.
But I'm just thinking that
No, that's fine.
it's fine, right?